Okay, today I will talk a paper about the overlap block motion application and the probabilistic integration with application of distributed rate coding. This is outline. For the introduction part, I will give a quick review about the distributed source coding, distributed radio coding, and then talk about the sign information independent and sign information dependent correlation channel modeling. And then we talk about the proposed overlapped block motion estimation and the probabilistic completion. Finally, show the result. For a quick review about distributed source coding. Distributed source coding is a compilation technology to comprise two or more correlated sources, and the sources will be encoded as an encoder separately, and sending the decoder, and at the decoder side will be decoded jointly. Distributed source coding shift the communication complexity from the encoder and decoder. So the decoder of the digital source coding has a very low complexity. Nowadays, or in the near future, the inexpensive video coding mechanisms is increasingly demanded, such as the applications, video sensor networks for security surveillance, and monitoring of the disaster zones, and some domestic applications like monitoring children and help the people by the guardians. And usually these applications need the lower communication and low power. But the traditional video coding algorithms, such as the 8.26 volt, are not satisfy this requirement because it has a very complex computation encoder. And since distributed source coding reduce the processing complexity and shift the majority computation from the encoder to the decoder, the distributed source coding is well established in the video coding. So the distributed video coding is ideal technology for the requirement capturing all the video streams from the remote side to the decoder, as mentioned in the above applications. The simplest distributed video coding frame is driven by the 1-0 theory, where the key frame is introcoded and available as decoder treated as that information, and the non-key frames will be 1-0 encoded and will be decoded with decoder with that information. Normally, there are two instantiations of the distributed video coding: the pixel domain encoding and the transform domain encoding. For the pixel domain encoding, the bitplines of the pixels will be compressed directly, but for the transform domain encoding, the pixels will be performed by a DVC transform, and then the transform coefficients will be grouped into the subband. Only the subband containing the most important information will be encoded, while the subband will few important information will be discussed. And usually the transform domain DVC will have a better performance than the pixel domain DVC. And in this slide, we will quickly review why the transform domain DVC has a better performance than the pixel domain DVC. Suppose we have a real image with size m by n, and here we only consider the 4x4 block of this image. And after a 4x4 DCT transformation, it will generate the DCT coefficient will group into the 16 subband, 1 DC band and 15 AC band. And since the information in the subband are not uniform, where the lower frequency band will have the much more information of this block. Here, the DC band has the most important information, and the AC, the 15 AC band will have the lowest information of the block. So now we can design. A weighted quantization matrix and allocate the allocate the large bit rate for the lower frequency band. Suppose we only keep the DC band and the first two AC band, and assign the 766 bits for the band respectively. So the
What's the meaning of the AC?
DC band. Sorry, I don't know the full name of the.
AC, I think is for some different frequency, different bases of
Something like AC and
exponential.
DC.
Yeah, DC is the, for example, average of all of the points, and AC is the from some exponential, different bases in the exponential that you can find, for example, the Fourier transform or something like that.
And you first you just sorted.
What?
You just vectorize that matrix and sorted.
You mean this?
Yeah.
Yeah, just here use the zigzag. How to say? The zigzag order for scan zigzag scan. So DC and this way DC 1, 2, 3, 4, 5.
Oh, something like
So that way the zigzag scan. So we can use the zigzag way. So if we find the 766 bit for the band respectively, the total compression bit is 19 bit.
And sorry, another quick. What's the meaning of what's the quantization matrix?
Quantization matrix is for each band you can assign different quantization level. You have a different quantization level. Here is this is a lower frequency band. It has the most important information of the block. So we assign we contest using more bit for this band, and if this band has lower important information, so we just discussed it.
For each band we have
the different quantization levels. So this quantization levels get together, we call the quantization matrix. However, for the pixel, if we only consider the 4x4 block, and we assume that the pixel, the original pixel is 8-bit integral, so the 4x4 block will need 16 by 8 bits for transformation. If to achieve the similar compression to the transform DVC, so we can quantize this pixel by the 19/16 to get the same compression. But we need to note that for here, we have not performed any compression technology, but only considered after the quantization step. So we can see that the transform technique has a better performance in the data compression because it removes all the redundant information.
And another question: the distributed video coding is one of the branch of the distributed source coding, or no, they are different?
We just use the distributed source coding in the video coding. Suppose we have the frame. Suppose we have two frames. One frame is a key frame. The other frame is called the interframe. Then we want to recover the interframe. So the key frame at the side information. So the interframe is encoded with some compression technology, and the decoder it will be decoded with the help of the side information. So this kind of technology is driven by the distributed source coding.
You use the distributed source coding for each frame of the video? Oh no, it has another method to just work on all of the video.
For each frame,
For each frame?
Yeah. Maybe during the following slides will be more clear.
Yeah, thank you.
And for the current distributed video coding works with both pixel domain and transform domain. they all assume that the correlation noise is independent of the realization of slight information. And in contrast of the current DVC work, this paper assumes that the distribution of the noise does depend on the realization of slight information. So based on this technique, the paper proposed a pixel domain omnidirectional DVC codec, which is a feedback channel-free codec and can achieve the similar performance compared to the state-of-art transform domain feedback channel-based Discover codec. Before I talk about the proposed model in this paper, we will first look at the sign information independent and sign information dependent correlation channel model. And in DVC, suppose we have two sources, X and Y. Y is considered as the noise version of the source X, and Y is corrupted by the digital noise. And so the correlation channel between the X and Y is defined by the probability density function, Fx given Y. So finally we can get is equal to Fn given Y. If the correlation noise is independent of the sign information, so the probability density function finally can be right in this volume, right as is equal to the Fn. It only depends on the correlation noise, and usually they assume that the correlation satisfies the Laplacian distribution. And if the correlation noise dependent the sign information, the probability density function also can write in the Laplacian distribution, but the only difference is that the correlation noise is a function of the sign information Y. So now we will talk about the proposed spatial domain in directional distributed weighting codec. And for the input video, we characterize into the GOPs and decompose into the keyframe and interframe. So GOP is we have the number some number of the frames, and one frame is called the keyframe, and the other remaining frames is called interframe. So suppose GOP is equal to 2. So for every 2 frames, one frame is called the keyframe. Keyframe will be encoded using the intracode.
And the GOP is the number of all of the frames?
No. Yes. Yeah. So for each group, this is decomposed in the keyframes and the interframes. For the anti-encoder, the keyframes will be intracoded. And for the interframes, suppose we have the capital M significant bit lines, and the capital M minus B, the M least significant luminance and all the chroma bit lines are discussed. Only the B luminance bit line of the interface entropy coded separately in different bit line by bit line. The residue of the significant bit line of BI will be entropy coded. So at the decoder side, since we're using the entropy code to encode the B most significant bit line inside of the China code, so as a decoder, we can get the correct decoded B luminance bit lines of the interframe. And as a decoder, we'll also have the correct information of the keyframe. But at the decoder side, we're missing the M least significant luminance and all the chroma bit lines. So the recovered interframe will have not good visual quality. So this paper, they propose overlap motion estimation probabilistic computation to recover the missing luminance and all the chroma bit plans.
What's the luminance difference?
Luminance bit plan because
What's that?
luminance represents the light of the
Yeah, you
the
need
pixel.
for each pixel you have different level of grayscale and you extract each level as a one bit map and try to code that.
For each pixel, it can have the one luminance and the two chroma.
Okay.
And for luminance,
In
we
the-
have the
Color space.
yeah. So for luminance and the chroma, they all have the capital M significant bit plan. But here at the encoder, all the chroma bit plans are discarded. So we do not consider the chroma bit plans. And for the capital M luminance bit plan, we only consider the first B most significant bit plan. We discussed the capital M minus B luminance bit plan.
And how you can find Z?
Z
Yeah, what's
Z is a here the differential bit plan by bit plan encoding the here for the frame SK and the previous frame SK minus 1. So we use the frame SK minus 1 because the residue and the residue will be entropy coded.
Z is the delay block. It's just the Z transform. It's delayed by one step. Then delayed by
Okay.
one frame.
Oh, the delay
So
of
we
the frame
delay
of.
yeah, so we subtract the last frame to it.
And for the another one is exactly what Z is that.
So I will go to the next slide.
Instead of RGB color space, there is some other color space like one luminance and like two components. And it's typical for image compression, video compression because it's more efficient memory. They can downsample the luminance component without affecting much the visual quality.
Question?
Top is PC.
This box is proposed algorithm. It's a short for overblock no transformation probability calculation. So I will talk this part later. This part is used to recover the missing the missing man, this Luna mismatch, all the chroma mismatch.
What is the role of the side?
This one.
Yeah, because I think that
This is
role
a-
here for the encoder. Yeah.
Here is a intro codec. You can use it's 1264 intro codec. This is the key frame.
Okay.
entropy encoder?
Entropy encoder. The Hamming encoder is a kind of encoder.
Entropy encoder is basically just lossless source code.
You mean if you code, you can recover exactly?
Yes, and lossless. And you compress up to the entropy level of entropy code. Theoretically. So, for example, like Hoffman or like alphabetic coding.
How is that the accuracy of this method? I mean that after decoder and after that
Here for
decoder,
you mean
how is it similar the input and output?
you mean right now?
Yeah, for this method.
Yeah. Right now, because use the entropy encoder here, use the inter encoder at the decoder side, we can correctly recover the input.
Do you mean that x and x hat are the same?
No, because here the B significant bit plan XB represents B significant plan. Here is a correct recover. It's recovered correctly because it used the entropy decoder. Here the keyframe is correctly decoded, but we said this is only about the B luminous bit plan. For each image, for each pixel, we still have the capital M minus B, least significant plan.
Can you say like psi has also usually correctly decode, or what do you say? Like lossless decode, you say? For psi hat?
You mean X hat?
No, psi hat.
Psi. Psi is a correctly decoded.
What's that? What do you say? Say that again.
Psi is correctly decoded.
Correctly, you said correctly
Yeah.
decode? What do you mean by correctly?
You mean the same psi hat and psi?
Lossless decode.
No, I mean it's not. It's like those H.264 is not lossless. Okay, I mean like you need to be very careful if this is your what should I say, company presentation like for interview. You already made several this kind of mistake, you're not going to get the job. Basically, like it just have a group of pictures. Psi is the key frame, and then X is the other frame that you want to count. You think of like each time you try to compress video, so you count like group them into numbers of group of pictures, and then you compress each group of pictures one at a time, and then like in a group of pictures, you pick one frame as an index frame, or maybe even more, but let's say here just one frame as index frame, and then you count, use conventional method to compress them and recover them. So that index frame is still lossy, and you use that index frame as side information to help you to decode the other frames. So the other frames are X here, and for the other frames, for the first big frame of the other frames, we are going to compress them losslessly with entropy coding. But for the rest, we are going to use distributed video coding. So this one choose the describe modes.
Okay, you mean in this proposed method, after applying this one, the psi hat it's equal with the others method, and we need to apply something for the interfere frames, interframe.
Okay, they just modify the other frame, the interframes, and how they encode the interframes. But the interframes, it doesn't what they are saying. Oh, I said they call it. They only modify how they encode the interframe, so the interference is they just use the conventional method, the digital 264.
We talked about overlapped block motion estimation, and for considered interframe, for a considered interframe, the previously decoded interframe or the keyframe will serve as the reference frame. Then, in the interframe and the reference frame, we choose the arbitrary size of block. Here we choose the B by B block. In the interframe, it is denoted by X sub B, and in the reference frame, it's called R sub B. Here, the S 0 and G sub 0 represents the top left coordinate of this block. And in the interframe, the interframe is divided into the overlapping spatial blocks. Here, the overlapping step size is epsilon. The overlapping spatial blocks X sub B, I 0 plus epsilon, J sub 0 plus epsilon. And epsilon smaller and equal than capital B, the block size B, and bigger and equal to 1. So for the block XB in the interframe, the number of overlapping spatial blocks is equal to capital B over epsilon.
You mean that if the distance of each point, 2 point is the 1,
here
epsilon is a 2 here?
Here is a pixel, the point is a pixel, and here I choose the 4 by 4 block. In this figure, it's a 4 by 4 block. If I choose the overlapping step size is 1, suppose I choose 1. So here, it should be a block, overlap block, and totally it has a 4 overlap block.
Yeah, but I mean that for epsilon. Epsilon has a 2 here.
Here, you believe right now?
Yeah.
Right now is 2, yeah.
Yeah, 2.
And in the reference frame, we define the third ring, and we want to find the best interframe block in the reference frame. And here, the matching criterion is minimize the bit error rate on the most significant bit length between the current block XB in the interframe and the block RB in the reference frame. And if we find,
yeah, I have question. Yeah. For this epsilon,
yeah.
I think now epsilon is for the horizontal and vertical is the same. But if the current interframe,
you mean we can shift the
we have the
vertical. But here I only show the one block in the interframe. If I have a block shifted on the left side by 1 pixel,
you have 2 epsilon.
So. I mean for this block, you mean?
Yeah, not for this one. If you just shift the second block to the epsilon is not same for the horizontal.
Yeah, I know what you meaning, but here if you follow this way, here I only show the one block in the interframe.
Yeah.
If I choose another block like this here. This block shift on the left side by 1 pixel, and we also use this same epsilon, so we can get the overlap block like this. it's a block. The second block shift on the left view side. Do you go?
But you mean that always we have just one epsilon, not the same number. For the horizontal and vertical is same.
You. Okay.
I mean that now it's something like that.
Yeah.
Yeah, here the same. If, for example, it was there.
Yeah.
This one is not same.
No. I mean, this is the concern. I consider this block right now. Then this is the overlap block for this. And if you find this block, then if you consider this one, you can find this block.
Okay, you mean
So you
always we have this epsilon and this epsilon the same.
No, the epsilon is some number between 1 and b. For example,
It
if
could
b
be
is
changed or
yeah,
not.
yeah, because I think they wanna find a lot of special blocks. For example, it can be different epsilon for the x axis or y axis.
Yeah, but I think
It's not
But I
only
think-
one block; it's set of blocks. I think
Yeah, instead of the block.
okay, it could be
Whole
changed.
With the-
way how.
with all possible epsilon between 1 and b.
So you should have two epsilon,
There
right?
are two epsilon, I think.
So
No?
what's epsilon 1,
I-
epsilon 2, right?
In the paper, it's a 1 epsilon.
Because
So-
the block size is b feet. Is the b for the
Something
x
you
and
said
y
it should
is-
be two kind of epsilon. But I think something that the Legion said it has to just one.
The
One kind of
paper-
epsilon. Because she said that if we just shifted one
Yeah,
one
the
pixel there,
The epsilon
That
is, I
should
think,
be
is not
here,
like
like-
one number. It's
I-
set of numbers between, or it's one number.
I think you can choose one number because when you how to say the block is moving all the image, and for each block you will find the maybe you're right. You will find all of the overlapping blocks. Then you can find all the overlapping blocks in the image. I can show you. This is the image, and suppose we. Yeah. This is the image. Suppose first we consider this block, and epsilon we take it equal to 1. So it's fallback goal. So it's a little larger than that. So I think for image, we consider this corner block, the fallback fold. So for the overlap block, we can find this three overlap block, and so the coordinate of the block denoted by the top left pixel, right? So after we consider this pixel, we will move to another pixel, maybe the second here. So now the block we consider that is this one. And for this block, what's the overlap blocks? Because the epsilon is still 1, so
then just one.
yeah, one. So finally, you can cover the whole image. I think because when I read the paper, I always think about it. They should have they should have the 2 epsilons. I think no.
I don't understand how.
Yeah,
So you
something
can only
that
go diagonal.
yeah, something that Julian said just one. It's
But
I think
why
it's
that's
weird.
weird?
Yeah,
That's too weird. Why you only
I think it
not
should
go
be
diagonal?
it should be just 2 kind of I think.
I don't think so. I guess most likely it's a typo in this paper. I mean, this sounds too weird.
He had the two kind of the similar paper. They also started this one
I mean,
so
the other,
the other paper, the same people.
but it's by the same people, right? Therefore
yeah.
they can make the same.
Same.
They basically just copy from.
Same mistake.
Yeah, when I read the paper, I think we should have the 2 epsilon,
Yeah.
but then we find the best match block in the reference frame. We will take this block at the sign information of the block XB in the interframe.
And how can find the next block? That's the
This
overblock.
block.
Yeah.
Here I have not talked about. I only talk about the if you choose one block in the interframe, you can find a match block in the reference frame.
Oh, okay.
So for each block, you can find a reference. You can find a match block in the reference frame. Then in the following, I will talk if we have so number of the overlapping blocks, how to deal with blocks in the reference frame.
No. I mean, yeah, my question is that which method they use for the finding the match block?
Oh,
Yeah.
In the circuit, you just find the block which is have the minimal the bit error rate on the most significant class. So if we find a best match block in the reference frame, actually this algorithm performs an estimation of the amount of the correlation probability P, XB, K given Y, K between the block XB and sign information YB by computing the 1 minus pixel error rate. Here is the delta function, and the pixels in the XB minus the co-located pixels in the YB. If they are same, the delta function is equal to 1. So the probability of the correlation can be interpreted as it equal to the number of the same pixels between in the block XB and in the block YB over the total pixels of the block.
Excuse me, the YB is that blocks you said? YB?
YB is a block in the reference frame. It's find the match block in the reference frame.
It should be shifted already, right?
Oh yeah. Here yeah. It should be other blocks.
Okay. What was the usage of the block in the current interframe?
The current frame, it means that in this frame we only have the B significant bit plan information for each pixel, and we don't know the missed significant bit plans and all the chroma bit plans. the reference frame is the previously reconstructed interframe or the key frame. It has all of the information of the
Okay. What was the blocks that you mentioned with the epsilon overlap? What's the usage of that blocks? You said XB is I0
Oh
plus.
yeah.
Has a Y.
This is the Y, or Y is in the second, in the reference frame.
In the Y
It's
is
just
a
something very simple. It's you just like do a default search of all the surrounding data and then find the overlapping.
So
Like
that's
this
external
process, and
search.
then like afterward do the estimation. Then with the reference frame is the shifted block. That's it. Yeah, that's in the last bullet, right? The best match with the reference frame surplus, the cycle
Yeah.
might be. So therefore, it can be like one epsilon, and it doesn't make any sense.
Yeah.
And it's only in one direction.
Yeah, that's exactly. It cannot be. Like, it doesn't make any sense.
Yeah,
It has to
it's
be like.
okay. It's like that. Because it covers all of the images.
So if we write the estimation of correlation probability in the vector general form, which is like the C sub 0 represents a vector pointing to the top left pixel in the block, and R represents a vector defined in the domain capital D, and we can write the correlation among correlation estimation of amount of correlation probability in the general vector form. And since we have a number of the overlapping blocks, so the each pixel in the interframe will belong to a number of the overblocks. For example, for the right pixel, in this figure, it belongs to the 3 overlapped blocks. And after we performing the overlapped block motion estimation, each block in the current interframe will find a best match block in the reference frame. Thus, the pixel in the interframe will be listed a number of candidate sign information pixels. So in this example, in this figure, the right pixel will be linked to 3 sign information pixel YK. And we want to recover the missing bit plan for every interframe pixel X. Here we use X hat capital M minus B to denote this. And we also calculated the correlation probability of the sign information block B on the last slides. So the estimated missing bit plan for the interframe pixel X can be calculated as a weighted average of the residual sign information pixel values. So here is the M missing bit plans of the sign information pixel YK, and this is the normalized probability of that information block BK. So take a weighted average, we can get the estimated missing bit plans for the interframe pixel X. Here, we should note that if after performing the overblock motion estimation, there will be pixels cannot find sign information pixels in the reference frame. At that time, the probability x bk given ybk is equal to 0. It means that there is no same pixels between the current block and the best match block in the reference frame.
No similarity to them.
Yeah, for the current block and the reference block, the located pixels are not same. So at this time, these pixels will be reconstructed by taking the mean of the surrounding reconstructed pixels. And by performing this algorithm for each pixel of the interframe, finally we will recover the interframe.
Excuse me. This figure, it was in the background?
No.
Because I have problem with the breakpoint.
Yeah. No, this I draw these figures because in my understanding, if we choose if we choose this block, this light blue block, and we want to find the best match block in the reference frame, so I suppose the best match block is here, and the pixel, the right pixel in this block, the position is here. So the co-located pixel is here.
Yeah.
So
But
for the
rest of-
second
yeah, I think
and third, this second, this is the sign.
it must be.
Maybe I make
You draw it correctly.
maybe yeah.
Yeah, I think you must change the
Yeah,
breakpoints.
I make mistake here. Should be here. Yeah.
Yeah, it's depend on the block that you find. I think you must find the location of the pixel.
Yeah, find the co-located pixel. Yeah. Yeah, and here is the result. In this table,
And another question is, you said maybe we have some pixel that we did not find any reference
yeah.
pixel for the why it happened.
Because how to define the best match blocks in the reference frame? They just because for this block it only contains the B significant bitline information, and this block in the block in the reference frame also contains the B significant bitline information. So they just take the bit error rate of the B most significant bitline. If they this P is calculate the P probability XB given by BK is calculated according to this equation. So if XB is equal to YB, the pixel in the block XB equal to YB, the this function equals 1. If they're not equal to pixel, the this function equals 0. So it can happen that the block doesn't have the.
Yeah.
So the result, first result. For this column, it's calculate the KL distance between the partial knowledge and the actual partial channel estimation and the actual channel estimation. The partial channel estimation it only contains the B significant bit one. So for the part A, B is equal to 1. It means only keeps the first significant bit 1. And B, for the part B, it only contains the first two most significant bit 1.
Excuse me. Is it pace, something like pace an hour?
The KL distance.
Is it distance?
KL distance.
No, I mean that something like the pace an hour. We have the formula. What's the formula for the finding?
Excuse me.
Which yeah.
What's the KN distance? KN.
Oh, KL. The Kurbach late one.
It's a probability of P
There's the Kurbach divergence.
in the information theory.
Yeah, by the time you guys graduated from PhD, like the questions that you ask around in this session, you should know that. Otherwise, if you go to a job interview, like you may have trouble. But it's okay now. It's okay. By the time you're prepared for job interview, you're supposed to know all this by heart. Now ask as many questions as possible. That's good.
they compute the KL distance using here the possibility density function f x given y. The experiment take the KL distance between the experimental f x given y and the partial channel estimation f x given y. And for this column, it calculates the KL distance between the actual channel estimation and the proposed and the estimate with the proposed algorithm. So from these values of 2 columns of value, we can see that for the proposed by using the proposed algorithm, the KL distance has a remarkable job. So it means that the proposed algorithm has a good performance for estimating the slight information dependent correlation channel.
How fast is that this method?
In the last slide, it shows the encoding and decoding time. And here is give the similar comparisons in terms from the point of the visual quality. And the figure A is the initial interframe, which only contains the first 2 significant bit plan of luminance. And the figure B is the reconstructed video frame by using the proposed algorithm, which recover the missing bit plans and all the chroma bit plans. And C is the original frame. So from these figures, decided only introduce hardly noticeable motion artifacts in the areas with irregular motions. And this result gives a comparison between the proposed algorithm with the discover codec. Here, the proposed algorithm with the sign information dependent channel estimation has similar performance with the discover codec. But the proposed algorithm with sign information independent channel estimation will have poorer performance than the discover codec, and then the proposed algorithm with sign information dependent channel estimation. So from this result, it reveals that the proposed algorithm depends heavily on the sign information dependent channel estimation. And this result take the comparison between the proposed algorithm with the H.264 intra codec, and it also shows the compatible or superior performance. And the result gives the comparison between the computation complexity between the proposed algorithm and discover codec, and it evaluated the complexity by using the based on the encoding time and the decoding time. So we can see that for the proposed algorithm, the encoding time A represents the encoding time and the part B represents decoding time. So the encoding time is very low. The reason is that the proposed algorithm does not have the channel coding, and they not do the DCT transform. But for the decoding, the proposed algorithm did not get the lower, did not have the lower time, because both of the codec have the decoding latency. For the discover codec, the decoding latency is the repeated channel coding and the feedback channel. But for the proposed algorithm, the decoding latency is sign information dependent estimation, and which mainly depends on the two parameters, the overlap step size and the search region in the inference frame. So that's it.
So sign formation is dependent why the capacity is so low for decoding.
Because it will sign information dependent.
Independent.
Yeah.
What did they do there? Decoding.
Because sign information independent, if you find the best match block in the reference frame, then the block will be taken as sign information. But for the sign information dependent coordinate estimation, you will find several match block the sign information. So you need to take the error rate.
But you still do the kind of the motion estimation of the decoder, right? You still look at each block and see which block is. Do they do the motion estimation of the decoder? Like basically the block correlation, the site information in the decoder case. Do they look for the block that have like highest correlation? No, they just use the block.
They use block, use the side the minimum error rate. That's the block.
But then they still need to scan through the whole.
Yeah.